Welcome back, critical thinkers. Well, now that we've had our first exam, we're starting a related topic. We're really going to, our last topic that we covered before the first exam was deductive reasoning, which was a way of testing reality-based questions. It's a tool in our toolbox about how to put our ideas together, right? If you deductively reason correctly, means you use the correct logical form, right? But how did we figure out what was true? Well, that was making sure we had the correct logical form and our premises were true. And deduction can't help give us a guide for how to figure out if premises are true. Deductive reasoning is for figuring out whether or not we've put our facts together in the right way. Inductive reasoning is how we figure out what the facts are. So make sure you have the lecture entitled Inductive Reasoning. And today we're going to refresh our memories about what induction is. It's really all about observation. And then we're going to learn about how to make the best observations to figure out what's true about the world. And the best observations are science. Yay! So this class is going to cover the basics of scientific exploration, the scientific method. Because if we're going to figure out what the facts are, the best way of going about that is science. And so we're going to learn the basics of scientific methodology. But first, let's go over again what inductive reasoning is. So starting at slide 1, I just make a joke about, what inductive reasoning is really about observation. And sitting in our chairs and only deductively reasoning, only putting our ideas together in the right way is really only half the story. We do actually have to go out there into the world and observe the world. And that is inductive reasoning, making observations. So if we think about our first forum activity, where great discussions ensued, the police gathering facts was the inductive piece of that. What we did with those facts to then rule Elaine out was the deductive piece. Figuring out what the crime scene is like, doing interviews, doing those observations is the inductive piece, putting those ideas together in a deductive way that allow us to conclusively rule Elaine in, because we could rule the other 5 women out. That was deductive, because we could say there are only 6 women who could have done it. 5 of them can't, so who are we left with? Only one person. So we identified Elaine as our suspect deductively, right? But how did we come up with the facts? How did we figure out the fact that certain women couldn't do it? Based on observation, based on good interviews and good observations. And so that is the inductive piece of figuring out what's true. So moving on to slide 2. We have inductive arguments, right? This whole class is centered around issues, reasons, and conclusions, right? Deduction was about using arguments to test our logic. What kind of argument? A very special argument called a logical syllogism, right? A logical syllogism. And so inductive arguments, on the other hand, are about how we figure out what those general rules about the world are. How do we figure out what the facts are inductively so we can put those facts together in the right way deductively? So inductive arguments are really going to be about observations and what makes a good observation different from a bad observation. That's what we're going to have our discussion today, as well as our next discussion on research methodology. So, okay, when we engage in observation, it's not going to be the same thing as we did when we did it deductively. We're not going to be trying to figure out what is certainly true if we could just agree on the facts. If we could agree that all turtles are green and we can agree that the animal in front of me is a turtle, then what certainly must be true? Well, I guess that animal is green. That's not what induction is all about. Induction is about what must be true if we can agree on the facts. Can I put my ideas together in the right way to discover what must be true? Certainly. No. This is how we agree on the facts, and we can never have 100% certainty. Why? Because we don't have perfect observation. When I go out into the world, even if I engage in excellent scientific methodology, I'm never going to have perfect observation. I'm not going to be able to be at all places at all times and know all things. And so the facts based on observation will always have some probabilistic component. For example, if I see if I see 1 swan, 2 swans, 3 swans, 4 swans, 5 swans, and I see 1,000 swans, I might start coming up with inductively some general rule about the world about swans being white, right? And if all swans are white, I discover or I determine, and this animal in front of me is a swan, I might then conclude, then this animal must also be white. But what happens to my inductive argument the minute a black swan comes swimming across my path? Boom! There goes my inductive argument, right? Because I've been able to disprove it. I've been able to falsify. That's what that word means. Falsify. It means to disprove. I've been able to disprove my inductive argument. And all observations have to be what are called disprovable, right? I have to be able to disprove it. And if I can't disprove it, well, then maybe that lends some good evidence to my point of view. So, for example, if I see 2,000 swans and they're all white, and then 3,000 swans and they're all white, I start coming up with a pretty good conclusion inductively. And so the strength of an inductive argument is going to be based on the quality of the evidence that I observationally gather. So moving on to slide 4, let's just try to illustrate again the difference between induction and deduction. So I'm driving down the road, driving down the road, and my car hits a bump, boom, and my car misfires. My engine goes boom. So I'm driving down the road, cycle, driving down the road, and I hit a bump, boom, my car misfires. I'm driving down the road for miles and miles and miles, and I notice that my car doesn't misfire. What about that? And I'm driving down the road, go over yet another bump. Boom, my car misfires. What is your conclusion? Maybe the bumps are causing my car to misfire. Did we need 1,000 observations to make that conclusion? No. We started generating a pattern about the world based on observation. And that's what scientists do. They make observations about the world, and they come up with some observable pattern about the world that then they push back at to see if they can get it to falsify, if they can disprove it. That's how science gets done. Because let's say I drive down the road some more, and I go over a 4th bump, misfire, drive down the road, 5th bump, misfire, drive down the road, and then I go over another bump and my car doesn't misfire. Well, maybe misfiring isn't always caused by a bump, or maybe going over bumps doesn't always cause my car to misfire, right? But once you start seeing a pattern of 1 bump misfire, 2 bumps misfire, 3 bumps misfire, you're coming up with some observable pattern that you're then inductively coming to a conclusion about based on the quality of your observations, if that makes sense. Deduction, on the other hand, is once you can agree on the facts, putting those facts together in a reasonable way to then come to some 100% certain conclusion. So here's my premise. A horn in a car is powered only by the battery, right? Well, I would probably accept that is true. That horns, being electrical in nature, are probably only going to be powered by the electricity coming from the battery. There's no other source of electricity in a car, so the horn must in fact be powered by the battery. Now I tell you the battery is dead. Does my horn work? No, of course not. We have logically deduced with deduction that if it is true, horns are powered by electricity coming from the battery, and if it is true that the battery is dead, then I guess the horn doesn't work either, right? And that's the difference between induction and deduction. If I accept it's true that horns can only be powered by batteries, and if I accept that it's true that the battery is dead, I have to conclude that the horn doesn't work. Induction is always probabilistic. Since I have gone over 10 different bumps, and every single time I've gone over a bump, my car has misfired, I come to the probabilistic conclusion that my car is probably misfiring because of the bumps. But if I go over more bumps, let's say bumps 11 through 20, my car doesn't misfire, then I guess it was a coincidence, right? And so induction is all about observation, which is disprovable. It's falsifiable. And so science is both. Science is good quality induction, where you make excellent observations, where you come up with general rules about the world that are probably true, and then put those ideas together in a deductive way that makes sense. That's what it is. All science is just issues, reasons, and conclusions. They're just scientific questions where you gather reasons inductively that are your evidence, and then you use that evidence to come up with a sound deductive conclusion. And that is what we're going to learn for the rest of today and next time, all about the basics of scientific experimentation. So moving on to slide 5. So when we consider observation, when we consider science, scientific observation, we're always going to be talking about probability. The only time we can talk about things for certain in science is when we have some mathematical model that perfectly predicts what's going to happen. Then the math is like deduction, right? Well, look, this equation tells me perfectly in terms of deduction. I have mathematically deduced that this is true. But science that does observation, where I'm gathering observations from these group of trees. Let's say I'm looking at fertilizer. Observations from these group of people, because I'm a psychologist. Observations from these group of chimpanzees, because I'm a primate scientist. Either way, whenever you're making observations, you're going to gather good quality evidence that provides strong support for your inductive conclusion. Not necessarily 100% certain, but now good quality evidence gives more weight, so you're more likely to believe it than 100% certainty, right? That doesn't mean we're not really sure, right? For example, theory of evolution. We call it a theory because we can't observe all places and all times. But based on our very detailed observations of the fossil record, we are pretty darn sure that evolution is how it works. And it's consistent with our deductive reasoning arguments. It makes sense, right? Not only do the observations inductively suggest that evolution happens, but it is deductively valid in terms of putting our ideas together in a way that makes sense. And so both of these together provides good quality argumentation for the nature of evolution. But we can't be 100% certain. No. It could be a vast conspiracy on the part of spaghetti aliens to make it seem like evolution is a thing by implanting fossils into the ground in an alien conspiracy. Is that likely? No, right? Based on our good quality observations, the fossil record seems to suggest that evolution happens, natural selection happens, that slowly over time some traits get selected for that allow the animal to be more fit in that environment, so they're more likely to survive and thus more likely to have offspring. They hand those traits off to their offspring, and thus those traits that help that animal survive get passed down from generation to generation. And every once in a while there's a mutation. We know this observationally, inductively, and sometimes it makes deductive sense that sometimes those new mutated traits would be good for the organism. And then sort of the accumulation of all these baby tiny changes then results in species evolving over time. So we've got the good fossil record to back us up inductively. Can we be 100% certain about where these fossils came from? No, but it's high quality evidence based on excellent induction. Moving on to slide 6. So when we are evaluating evidence inductively, we are going to focus on the quality of the evidence. And there's a lot of ways to determine good evidence from bad evidence. And for the purpose of this class, we're going to focus on how do you know good science from bad science, right? Because scientific methodology is the best way to go about making observations. And so scientific methodology is the best way to engage in induction. And also, once you learn the language of scientific methodology, it becomes a lot easier in your everyday life to sort of use these tips and tools to make good observations for yourself, to not be biased, to weigh evidence against each other. And so we are going to learn how to evaluate good science from bad science, because induction observation is only as good as the quality. How good is the evidence, right? And so the conclusion when you make observations is only as good as the evidence that you gathered based on your observations. And so high quality evidence then supports the conclusion. And so when we gather, so moving on to slide 7. So when we gather evidence out there from the world, our goal is to use that scientific methodology to do something called generalization. Because what we're really trying to do in scientific methodology is generalize from what we see in individual observations and then generalize it and come up with big rules about the world. And so just like deductive reasoning was using big ideas that we already knew were true about the world and going top down, going from the general rules to making decisions about the specific case, the general rule that all turtles are green, the general rule that this animal in front of me is a turtle. My specific conclusion, top down, that this animal is green. We're going to back up and sort of flip that around now, because this is the other piece of that scientific puzzle. We're going to say, what can I observe about the world, about individual frogs or individual turtles, to come up with some generalizable big ideas about turtles everywhere, or frogs everywhere, or people everywhere, or trees everywhere, or electrons everywhere. Science, induction, is how we come up with these big general statements where we can say, it is true that on average, people who are more attractive make more money. Guess what? That's totally true. Does that mean there are not some people who are unattractive that make a lot of money? No, that is also true. But it is true that I can generalize based on my observations. Person 1, person 2, person 3. I gather evidence. And then I can say, well, in general, on average, I can see that being much more attractive gives you sort of an edge in terms of income, right? And so that's sort of the goal of science, is to come up with these general rules that then can be derived and concluded inductively, so then we can use them deductively to make decisions about the world. And to do this, we make high-quality observations based on good research methodology, and then we do this thing called statistical analysis, which we won't do in here, at least not very much. So moving on to slide 8. What is then research methodology? Because this is the gold standard. If you want to make a good observation about the world inductively, if you want to decide what the facts are, so that you can then put those facts together in a sound, valid, deductive way, scientific methodology is the way to go. So what is then the steps of research? The steps of research. Well, there's 5 broad steps of research. 5 broad steps. The first is to figure out what you want to study. It's called identifying a characteristic of interest. And this being Psychology 66, let's just talk about people. Let's say I want to identify some human characteristic that I'm interested in. All right. So let's say I identify depression. I'm interested in figuring out some facet of depression. All right. So then I have to decide, okay, well, who do I want to know about? Do I want to know about depression in adolescents? Do I want to know about depression in women? Do I want to know about depression in children? Do I want to know about depression in dogs? Do I want to know about depression in people everywhere? This is step 2. Identify what's called a population of interest. And so a population is everyone you're trying to make a decision about. Number 3, figure out who you can actually get data from. Figure out who you can actually coerce to come into your psychological lab and answer your questions, or come into your psychological lab and take part in your experiment. Figure out who you can get to answer your questions. This is called, hopefully, a representative sample, a group of people that are meant to represent your entire population well. So let's say I'm interested in depression in adolescents. My characteristic of interest would be depression. My population would be adolescents everywhere, all, some 1 billion adolescents on the planet. But I can't get all billion adolescents on the planet, so I decide to grab a sample of 200 adolescents. And hopefully those 200 adolescents are going to represent that whole population well. And so we would call it a representative sample. That's step 3. Step 4 is to actually collect some data, like sit down and have some, systematic interviews with these adolescents where they tell me all about their depression. Tell me about your grief. Tell me about your feelings of guilt. And I gather detailed accounts all about adolescents' experience with depression, right? And if I do it in a systematic way, then I can get some good quality data. And the last step is, once I've gathered that information from those adolescents, we call this information data. Any answer they gave me to a question is data about them. Then I'm going to do some statistics on that data, right? And statistics is just a way to look at people's answers to questions and then figure out whether or not their questions reveal something about the characteristic of interest. For example, data. So you should just think of it as fancy math. Fancy math that we do on data to figure out whether or not our conclusions are statistically valid. So those are the 5 steps, right? The inductive piece of this is 3 and 4. Actually gather some people and collect some data, make some observations about them. The deductive piece is then 5, right? Where I actually do some statistics on my data and then deductively figure out what is true based on my observations. For the rest of this lecture, we are only going to focus on steps 3 and 4. We are going to, really steps 3. We're going to focus on how do you get a good sample. Because research, first you got to sit down and think about what do I want to know about, come up with a good characteristic, and then you got to figure out who do I want to know it about. And so then you have to figure out how can I make sure that I grab a sample of people that are actually going to give me accurate answers. And so for the rest of today, we're going to learn the basics of good sampling procedure. And so that is going to be the rest of today, the rest of this video lecture. I guess you don't have to watch it all in one day. You could watch it in multiple days. But for the purpose of today's unified lecture, the rest of today is going to be on how to get a good sample. And so moving on to slide 9, first, let's start with a joke. All right, so we are currently on my joke, which is on slide 9. So here and I actually did make up this joke. I stole that picture from the internet. I borrowed that picture from the internet and I made up this joke. I'm sorry, honey, I just overheard you say during the last election that all those pollsters couldn't really predict what the population of voters would do based on a sample. So when they came to take a sample of your blood, I was sure you would want them to take it all. Why is that funny? And why do I tell this joke? I tell this joke because I think a lot of times people think about what samples are and they go, well, scientists really don't know anything because they just get samples of people, right? They just grab 100 people, and what can you tell from 100 people? And if nothing else, at the end of today, I hope what I will leave you with is the understanding that as long as you engage in good sampling procedures, small group of people can totally mimic large groups of people. And so the big message that I want you to have at the end of this discussion is that if you use careful, known, learnable, systematic procedures, researchers can use small groups of people to make decisions about large groups of people, to draw conclusions about, make decisions about. And so we're going to learn sort of the basic terminology of research methodology. And then we're going to learn the basics of sampling. This idea that if we take a small group of people from a large group of people, as long as we do it in the right way, that small group of people should look like that large group of people. So slide 11, some vocab terms that you need to know. So people can be different from one another. What do you know about that, right? People can be different in terms of height, weight, race, gender expression, the color of car that you drive, your aggression, caffeine intake in a day. There are theoretically uncountable ways, a multitude, uncountable ways that people can be different from one another. The number of hairs on your head, if that interests you. We call the characteristics on which people are different variables. They are ways that people can be different. That is a variable. For example, height, weight, race, age, caffeine intake. Because these are characteristics on which people vary, right? That is a variable, some general characteristic on which people can have different answers when you ask them, hey, how much caffeine do you drink in a day? Hey, what's your gender? Hey, what's your biological sex? Hey, what color car do you drive? That question is the variable, and people have various answers. So gender is a variable, and then there are multiple possible answers. I'm male, I'm female, or I'm a man, I'm a woman, I'm gender fluid, whatever it is, I'm transitioning, whatever it is, the answer to the question is not the variable, the question is the variable, because that's the human characteristic on which people can differ. What color car do you drive is the variable, car color. I would answer that question green. Green isn't my variable, because that doesn't vary for me. I own a green car. That's my answer to the question, what is your car color? The question is the variable, that human characteristic on which people can be different. And you can even experimentally manipulate variables. For example, if I want to determine if exercise increases weight loss, then I've got a couple of variables there, right? Exercise. How much exercise do you engage in? Weight loss. Another variable. I can tell 50 people, you exercise. I can tell another 50 people, don't exercise. How much you exercise is then a variable. People's answer to that question, or the group I stick them in, is something called their outcome. It's the answer to the question, right? So you think of some variables. You think of some variables on which people can be different, right? And sort of practice doing that. It's just a good exercise to do, right? There's lots of ways for people to be different, and we call those variables. Moving on to slide 12, every research question about people that has ever been asked, ever in the history of ever, has always been conducted on variables. We don't conduct research on things that don't vary between people. We don't do research on whether or not people have DNA. Why? Because it's not a variable. All people have DNA. We might do research on different patterns of DNA because that's something that can vary. Patterns of DNA. For example, another example, if I'm interested in student success, I'm not going to do any research on whether or not someone is a student. That wouldn't make sense. If I'm only interested in students, then that's not a variable. If I want to do research on whether or not students are more likely to make more money or less money, now students has become a variable because I'm looking at students versus non-students. So a variable is a human characteristic on which people can be different in terms of a research question. That is a variable. And so here's some examples of research questions and the variables that underscore those research questions. And these are questions that a psychologist or another behavioral scientist, like a sociologist or an economist, might ask. What is the average IQ in adults? That's an interesting question. In this question, being an adult is not a variable because I'm only interested in adults, right? What is a variable? IQ. Because among adults, IQ can vary. Some people may have high IQ, some people may be low, but in terms and in reference to this research question, IQ is the variable. Does age impact cognitive functioning? Well, age is a variable in this research question because I'm curious if people with higher age or lower age have different cognitive functioning. So age is definitely a variable. But also cognitive functioning, right? People have more versus less cognitive functioning, their ability to think well. That's what cognitive functioning means, the ability to think well. And so when I ask the question, does age impact cognitive functioning? The two variables are age and cognitive functioning. Now, I would answer these questions 37. I'm 37 years old. So age is the variable, 37 is my outcome. So let's say I have poor cognitive functioning because I'm getting older and it's all downhill after 25. So I would say, well, I have medium or declining cognitive functioning. My answer to the question, medium or declining, is my outcome on the variable, how much cognitive functioning do I have, right? So those are the variables. And all research questions address variables, characteristic on which people can be different. We don't study whether or not people are from Earth, right? That's not something we research because all people that we've met so far are from Earth. So there is no research questions out there to say, what is the nature of people from Earth, right? It's just Earth status is not a variable because we all live here on Earth. But however, they sent someone off to spend some time for a very long time in space, and they actually saw how space impacted his functioning. Living on Earth for a while, living versus in space in a while, that would be a variable. Does that make sense? Hopefully it does. If it doesn't, please use that forum down there to ask any questions about this topic that you might find confusing. Moving on to slide 13. So then let's sort of broaden our understanding. So we've got research questions that we can ask about the world, research questions we can ask about people, interesting questions about people. Research questions are always about variables. They're about ways that people can be different and really asking the question, well, how are people different? Or why are people different? Or what is the nature of human differences? These are the kinds of questions that you can ask as a researcher. But another thing you need to know is all research questions are about populations. Because if you remember those 5 steps of research, the first thing is to identify a characteristic of interest. That's really identifying your variable or variables. Identify some set of human characteristics that you're interested in exploring. That's identifying your variable. The second step of research is to identify what's called a population of interest. That means, what are all the people you're trying to make a decision about? So here's an example of a research question. Do people over 55 vote in greater numbers compared to people who are 18 to 55, right? So we've got a variable, age, right? Where I've chunked people into 2 broad groups, over 55 or those potential voters 18 to 55. So that's a variable, age status, over 55, under 55. But also, so that's a variable. But listen also how that creates 2 populations. So I've got these 2 now populations that I'm trying to make a decision about. I'm trying to make a decision about all people over 55. I'm also trying to make a decision about all those people 18 to 55. So I'm looking at the populations of voters 18 to 55 and then the population of voters over 55. Now, those become my populations. Those people are my populations that I'm exploring the differences between the variable age. So what is a population? Well, it's all those people that you're trying to make a decision about. So once again, if I'm trying to decide what depression is like in adolescence, the variable that I'm interested in is depression. The population that I'm interested in is adolescents, right? And different research questions can have more than one variable. Different research questions can have more than one population, right? But your populations of interest are always all the people you're trying to make a decision about when you're trying to answer a research question. So let's see if we can sort of take a little quiz here, right? So we've got which freshmen are more enthusiastic on slide 15. Which freshmen are more enthusiastic about their school? Those at Pierce College or those at Texas A&M? Well, what are my populations of interest? Pierce College freshmen and Texas A&M freshmen, right? And I have a couple of variables here. Well, I have where do you go to school as a variable, but also enthusiasm, right? Those are the ways that people can be different. And so I'm really looking at these two different populations. Pierce College freshmen, Texas A&M freshmen, and because I'm looking at two different populations, I also have that as a variable. Where do you go to school? But recognize I have another variable too, enthusiasm. In the U.S., are there more people with depression living in urban versus rural areas? Well, how am I going to determine this? What I'm probably going to do is look at all the people in urban and rural areas and compare. Are there higher rates of depression? Right? Are there more people with depression compared to the people without depression in these areas? So my populations of interest become all the people living in urban areas, not just the people with depression, because I have to compare those people to the depressed people, and all the people living in rural areas, comparing the depressed people to the not depressed people. Because of how I asked the question. I asked the question about, are there more people with depression compared to not depression living in these areas? So I'm interested in all the people in urban and rural areas. Now, if I'd asked a slightly different question, let's say if I had asked this question, is depression more severe in urban versus rural areas? Well, that's a very different question, right? It's related. I'm still interested in depression. That's the characteristic that I'm interested in. And I'm still interested in urban versus rural areas, but now my population has shifted because I'm only interested in the people who have depression, and now I'm looking at how severe that depression is in urban versus rural areas. And so this is sort of an important thing to point out about scientific research questions. Depending on how you, the researcher, asks a question, can shift and change the population, can shift and change the variable you're looking at, right? You as a researcher are free to ask any question that you want, which is, kind of awesome about research. And now here's the hardest one of all. Who will win the 2016 congressional election in California's 3rd district? That's the hardest one of all. Now, who are we trying to make a decision about? And yes, we're trying to make a decision. We're trying to make a decision about who's going to win. But do the candidates decide who's going to win? Do the candidates decide who's going to win? And you can put any year you want in here at all. Who's going to win the 2018 congressional election in California's 3rd district? Who's going to win the 2020 congressional election in California's 3rd district? Who's going to win the 2050 congressional election in California's 3rd district? Either way, who are we trying to make a decision about? The candidates? Well, yes, but only indirectly, right? Because how do we decide which candidate wins? Is it all the registered voters? Is it all registered voters that decide who wins? No, because not all registered voters show up that day, that November day, that Tuesday in November. That's when we vote, guys. No, we're trying to make a decision about the actual people that are going to show up on that future date. Do we know who's going to show up on that future date? No, we don't. But political posters try real hard to try to figure out who those people are going to be, right? And so the population is actually unknown specifically. So political posters actually do this thing where they try to identify what's called a likely voter, and they use that as their best guess of who that population of voters might be. They grab 2,000 people and they call them likely voters. And a likely voter is someone who is registered to vote, who has voted in the last election, and number 3 says they intend to vote. And actually, research suggests that those people who answer yes to all 3 of those questions, yes, I'm registered, yes, I intend to vote, and yes, I voted in the last election, are actually highly likely to vote in the upcoming election. And so that's their best estimate of who that population might be on that Tuesday in November. So, slide 16. And so research questions are always about variables. They're always about ways that people can be different, looking for patterns among ways that people can be different, like who you're going to vote for, totally a variable, right? When I answer that question, that's my outcome, not my variable. Who I'm going to vote for is the variable. I might be interested. Do Republicans and Democrats, are they going to vote for different people? So now I've got my vote. Now I've got my populations of interest. I've got my populations of interest, Democrats versus Republicans. Do I care about independence in this research scenario? No, I don't. Don't care about independents in this scenario. I want to know, is there a difference in voting patterns of Democrats versus Republicans? So I've got my 2 populations, Democrats and Republicans. That's also a variable in this situation. Are you a registered Democrat or a registered Republican? Is a variable. And that creates my 2 populations based on my research question. Another variable is who you're going to vote for, right? And so all research questions are about populations, the entire group of people you're trying to make a decision about, and about human characteristics on which people can be different. Hopefully that makes sense. But as behavioral scientists, we don't often have access to entire populations. As a political researcher, I might be interested in Republicans and Democrats everywhere in the world. I might be. But I don't have access to all the Republicans and all the Democrats living in the United States. I simply don't. I don't have access to those people. So what do? Let's say I'm an aggression researcher and I'm interested in aggression in children. And I don't have access to all the children who live in, let's say, the U.S., because I'm only interested in children living in the U.S. So my population of interest is children living in the U.S. Can I get all the children living in the U.S.? No, I can't. I can't do that. I can't get all the children living in the U.S. to answer my questions. I just can't. So what am I going to do? Am I going to pack up my bag and go home and say, oh, I'm so sad. I'm so sad. I can't do research anymore because I don't have access to populations. Of course not. Of course not. What we do instead is something called sampling, right? What we do is we engage in systematic sampling procedures where we try to use a small group of people to make decisions about a large group of people. Now, who's that large group of people? My population. The population I'm trying to make a decision about when I ask a research question. The sample is that subgroup of people that I hope, if I do my job correctly, are going to represent that population well. Now, does that mean researchers never have access to populations? No. Sometimes we do have access to populations, but that is hard. That is called a complete enumeration. That is called a complete census. Synonyms for the same idea. And if you can do that, more power to you, but usually with most research questions, we're interested in a large enough group of people that we don't have access to a complete population. In fact, a complete census of all the people in the U.S. is only done every 9 years and requires millions and millions and millions of dollars in the resources of the federal government. Yeah, we can't do that as behavioral science researchers usually, right? Usually our populations are not narrow enough that we can ask every single member of that population any questions. If we can, that's powerful, but usually we can't. And so let me give you an example of a very simple research question that it would be impossible to ask every single member of the population a particular question. So there are 3,820,269 adults living in the LA area, according to the last census. That is a lot of people. How long would it take for me to ask all 3,820,269 adults living in LA a single question? For example, maybe I want to know, do men living in Los Angeles attend more theater production shows than women living in Los Angeles? Or vice versa? Do women watch more stage shows, or do men? Is there some gender difference here? I'm curious because I'm wondering if maybe I need to target my advertising a little better to capture both of those groups of people. If one group is not attending enough shows, maybe I can do better marketing. I don't know. How long would it take to ask almost 4 million people a single question? Let's time it. Tell me, how many shows did you watch last year? Quickly, 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 quickly. And then they think, right? And I'm standing there, and I'm standing there. Let's say they take 15 seconds to answer. So now I've got like maybe 30 seconds, right? 30 seconds. 400 million people, 200 million seconds, 200 million seconds divided by 60. How many minutes is that? Oh my God, the mind reels, right? We have so many people to ask that single question. I would need a whole lot more research assistants to walk around with their clipboards to ask 300 million, to ask 400, to ask that many people, 4 million people, even a single question, right? That's just crazy, right? That's just too many people. That's just a lot of people. So what do we do instead? My populations are men living in Los Angeles, women living in Los Angeles. All those people are my populations. I have a variable, gender. I have typically developed self-identified gender. I've got another variable, how many shows did you watch last year, right? But I can't ask that question to everybody. So what do I do instead? Moving on to slide 17, I grab what's called a sample, right? Instead of trying to ask that question to all 4 million people living in LA, instead, let's say I grab 500 men and 500 women. And as long as I grab those 500 men and 500 women in a very particular systematic way, those 1,000 people should represent those 4 million people pretty well, 3.82 million, right? And so what the goal of sampling is to then create what's called a representative sample. You want your small group of people to look like your large group of people. And to use our new vocab terms, we want our sample to look like our population. We want our sample to represent our population really, really well. So we want to gather what's called a representative sample, right? And it doesn't happen by magic, right? We know what can make a sample representative. Moving on to slide 18. So what we're going to talk about in here is a couple of problems of sampling, right? We're going to talk about what's called convenience sampling, and then a problem of most research, which is called voluntary response bias, which is sort of a problem whenever you ask people questions. And then third, we're going to go over the gold standard of research. If you want to make sure your samples look like your populations, you need to engage in what is called random sampling. And there's lots of different kinds of random sampling, and we're just going to talk about 2 types: simple random sampling and then stratified random sampling. So, convenience sampling, what is it? Well, convenience sampling is essentially grabbing people who are convenient to you from the population you care about. Let's say I'm interested in voting behavior, and so I decide to just I decide to conveniently walk outside my house and only talk to registered voters who live outside my house. Well, if I'm only interested in people who live by me, I guess that's okay. But if I'm interested in voting behaviors across the U.S., only talking to voters conveniently located outside my house is not going to give me very good information about what voters in the rest of the U.S. are going to look like. It's not going to represent that population very well at all. Essentially, what's going to happen is that I'm going to end up with a biased sample. Now, bias doesn't mean my sample is prejudiced against other samples. What it means is my sample doesn't look like my population. So there's another vocab term, bias. In research, what bias means, when we're talking about sort of the formalities of samples, bias is a technical term that means your sample doesn't look like your population. Your sample is biased. So let me give you another example. Let's say I'm interested again in political opinions. And so I decide to go out on the street in Berkeley because I'm happy to be staying in Berkeley. Or let's say I decide to go out on the street in Provo, Utah, because I happen to be staying in Provo, Utah, and I do a political survey. Now, if I'm only interested in what people are like in Berkeley, that might be okay. If I'm only interested in what people are like in Provo, that might be okay. But if I'm interested in voting patterns in general, those people are not going to represent my population well. They're not going to represent U.S. voters in general very well at all. I will end up with two different, very biased samples. And here's a dirty secret about psychology and other behavioral sciences like sociology and economics and other behavioral science disciplines. A majority of the research done in these disciplines are done on convenient samples. In these disciplines, most of the research, and I don't mean like 90%, but above 50%, a lot of the research is conducted on undergraduate psychology students enrolled in Psychology 1 because most psychology researchers are psychology professors. And the students are convenient to them, right? Now, what does this mean? Does this mean all psychological research is garbage? Of course not. What it means, though, is that any research findings that these professors stumble upon are going to be only most appropriately applied to undergraduate psychology students who attend major universities or attend higher education, right? And so, but you just have to be aware that not all samples are created equal. And so if you're reading a research article that makes some claim, your first tool in your toolbox as a good inductive evidence evaluator, because remember, inductive reasoning is about observation and scientific research is about observation. Your first tool in your toolbox in evaluating scientific evidence as inductive evidence is to ask, who was your sample? Who was your sample? Because whoever your sample was, those are the kinds of people you can make decisions about. If you get a convenient sample, that's not necessarily like doom and gloom for the research, but what it does is it constrains the population that those researchers can make decisions about. So always ask, who did you do your research on? Moving on to slide 20. Another thing to ask yourself when you're evaluating inductive evidence, when you're evaluating scientific literature, is to ask this question. How much was voluntary response bias a problem? Because whenever you're dealing with research with people, you kind of have to have them volunteer to be in your research unless you have a very, very unique research question. If you're interested in public behavior, like people crossing a street, or people picking up money off the ground, or people engaging and helping in a real-world situation, you can sometimes just be on a fly on the wall and just watch what people do, right? You can sometimes do that. But anytime you give someone a survey, anytime you call them on the phone and say, hey, can you answer and ask a few questions? Anytime you say, hey, can you take part in my survey or in my research study? They have to volunteer, at least in this country, right? You can't force people to take part in your research. And some research is easier to take part in than others. Right? If I stop you on the mall at Pierce and I say, hey, real quick, I just want to ask you one quick question, voluntary response bias, voluntary response sampling is less of a problem. Because if I say it's really only going to take 30 seconds, I have one question I want to ask you about tuition at Pierce, you're probably going to go, okay, I'll answer that question. It's only going to take 10 seconds, 15 to 30 seconds. So voluntary response sampling is just going to be less of a problem. But let's say the research is more intensive. Let's say I'm a newspaper person and I want a newspaper. It's ancient technology, right? That you have to open it. We do one here at Pierce, right? Anyway, let's say I'm a newspaper columnist, or let's say I'm an online magazine columnist, and I tell my viewers or my readers, I want you to write into me. I want you to go get a piece of paper, write me a letter, stick it in an envelope, put a stamp on it, put it in the mail. Wow, that sounds super hard. Getting people to volunteer to do that is probably going to be more difficult than getting people to stop and ask a few questions for a few minutes, right? And so voluntary response bias for that kind of sampling is going to be a bigger problem than if I just say, hey, can you answer a few questions for me? And the problem is, you never know what the people who didn't answer your question would have said. You never know what your unmotivated non-volunteers, what kind of answers they would have given you, because they might have given you very systematically different answers. And so here's a real-world example of this. Ann Landers is actually a newspaper advice columnist. She's a real one. She's kind of like Dear Abby. You would write into Ann Landers. And she actually did just this. She basically, in the newspaper back in the 80s, asked her readers to write into her. Say, hey, readers, can you please write into me and tell me how you feel about parenting? 70% of 10,000 people who sent her a letter. 10,000 sounds like a lot, right? But 70% of the people who wrote into her said they would not have children again. Well, that sounds incredibly depressing. That sounds like 70% of parents everywhere wouldn't have kids again. But check it. Think about the amount of effort it takes to go to the desk, get a piece of paper out, write a letter, because this is not an email. This is back in the 80s. Put that letter in an envelope, stick a stamp on that letter, go down to the mailbox. These are people with something to say. In fact, these are people with problems writing into an advice columnist or reading an advice columnist. These are people with problems with something to say. And who is motivated to send a letter about their feelings about parenting? The parents who are happy about parenting? No, the people who are unhappy about parenting. Because when we do what's called random sampling of parents, where we say, hey, quickly, can you just tell me how you feel about parenting? A good random sample of people, where we say, I want to get a good random sample of all parents everywhere, 91% of them would say they would definitely have their kids again, that they're happy with the experience. So you have 30% of people having to write a letter. So a voluntary sample, a completely voluntary sample where voluntary response bias would be huge. 30% saying they would have kids again versus 91% of this thing called a random sample where you try to minimize the amount that volunteering would be a problem for your sample. That is a very different story, right? When you get a good representative sample, 91% of parents would say they would do it again. A non-representative sample of only people who read Ann Landers, who are willing to write a letter about their feelings about voluntary response, about parenting, then you have a very different answer to the question. And so it's something to consider, something to ask yourself about the research. How much would voluntary response bias have been a problem in this research? Is the barriers to participation big? Are people not going to want to engage in this research? Or are the people most likely to volunteer going to look systematically different than the people who are not likely to volunteer? Because that was the problem with the Ann Landers situation. The people most likely to write in had very different feelings about parenting than the people who were not motivated to write in. So then what do you do instead? Instead of convenient sampling, instead of only trying to get highly motivated volunteers, what should you do instead? If you want a representative sample, what should you do instead? And the answer is random sampling. And it's also sometimes called probability sampling because here is what makes for a random sample. You put all of your population in a theoretical conceptual bucket, right? You take all of your population and you put it in a bucket. And then that way every single person in your population is in this theoretical people bucket, right? And there's some pattern in this people bucket. Patterns of age, patterns of extroversion, patterns of depression. And whatever you're interested in, you're looking for a pattern in that variability, right? The united colors of depression in my people bucket, right? so a random sample then is reaching in at random and pulling people out at random. And so you end up with a giant handful of people that their pattern of differences, because you grabbed them at random, is going to be the same pattern of differences as the bucket. Each person in the population has an equal likelihood, an equal probability of ending up in your sample. And here's how you could do it. Assign every single person in your population a number, and then start drawing numbers out of a hat. Number 17, you can be in my sample. Number 23, you can be in my sample. Number 67, you can be in my sample. And that is what's called simple random sampling. An even better style of random sampling is called stratified random sampling. And this is where you try to figure out as much about your population as you can. Figure out your gender breakdown. Figure out your ethnicity breakdown. Figure out your occupation breakdown, your religion breakdown. Figure out every single category that you can about your population, and make sure that if there's 50% men and 50% women in your population, make sure there's 50% men and 50% women in your sample. Let's say you're looking at happiness at a company, like work satisfaction, and 10% of the company are managers and 90% are frontline staff, right? In your sample, you're going to want to make sure there's 10% managers, 90% frontline staff. It's what's called stratified random sampling, where the different categories of people, gender, religion, work, your job, are different categories or strata. So, our first characteristic, if we want our samples to look like our populations, is our sample has to be random. Because think about it this way. Let's say I'm trying to figure out what what people think about, let's say I'm trying to figure out the average height in America, right? If I don't have a random sample, if let's say I just grab people in clusters, right? Let's say I go over to the gym and I grab a cluster of people there and go, oh, you're convenient, I'll grab you. And let's say then I go over someplace else and I grab a cluster of people. I'm not doing anything random. I could grab 30 basketball players. I could end up grabbing, 12 friends, all who are, shorter. I don't know, whatever. The basketball player, I think, was the best example, right? But if I don't do it randomly, there's some pattern in the bucket that I'm not going to capture because I'm not making sure that all the people in the bucket have an equal opportunity of ending up in my handful of people. It's got to be random. First characteristic of a good sample is that you have a random sample. Moving on to the next slide, slide 22. So, if you have actually sampled from the population you care about, you haven't done like a voluntary response sample, haven't done a convenient sample, but if you've actually sampled from the population you care about, and you've done so in a random way, then all things being equal, sample size matters too. That means bigger samples are better than smaller samples, right? And it doesn't have to be like some specific subset of the population, right? Like for basically just like 100 coin flips can reveal to you whether or not, or 1,000 coin flips can reveal to you whether or not a coin is weighted, even though you could theoretically flip the coin an infinite number of times. 1,000 is still pretty good. It's the same thing that works with people, right? Even if there are 7 billion people on the planet, if I truly randomly sample from all 7 billion people, no matter how big my bucket is, as long as I swish up my bucket so all the people are completely random in my bucket, even if I grab only 1,000 people in my handful out of 7 billion, my handful should still look like my bucket. I like to imagine candy. I like to imagine that like people are candy, and there's some color and size and calorie content and just variation in a big old bucket of candy. As long as I mix up the candy really, really well, it doesn't matter how big my bucket of candy is. As long as I grab a big enough handful, my handful should look like the bucket, right? And so 1,000 people is a fantastic sample, right? And 1,000 people is just going to be better than 100. 2,500 people, 2,500 people is a super fantastic sample. In fact, once you get around 2,500 people, no matter how big the population, that is usually going to be almost perfect representation of the population, usually. As long as you do random sampling from that population you care about, right? And so that is sort of an important point. A good sample is going to have 3 characteristics, right? Moving on to slide 23. A good sample is going to be a random sample from your population, right? That's important. Like, if I'm trying to figure out what policemen are like, getting a random sample of firemen wouldn't make sense, right? You do need to actually sample from the population you care about. And I say that because sometimes you don't. Sometimes researchers, they actually grab samples of people that actually aren't even from the populations they're trying to make decisions about, or include people that they're not trying to make a decision about, right? And that's a bad idea. Or let's say I'm trying to make a decision about LA employees. Should I only grab city council members? No, I haven't actually sampled from the population I care about. So if you want a good sample, you need to actually randomly sample from the population you care about. So if I'm interested in 20-pound dogs, I need to sample from 20-pound dogs. And how should I do so? Randomly. If I'm interested in belly dancers, I need to sample from belly dancers, not from hip-hop dancers, not from dancers in general. I need to sample only from belly dancers. And I should do so randomly. Then, if I do that, then bigger is better. 1,000 belly dancers is better than 100 belly dancers. But if I'm interested in belly dancers, 100 belly dancers is better than 1,000 hip-hop dancers, right? So it's in order of importance. First, you have to randomly sample from the population you care about. If you do that, then bigger samples are better than smaller samples. And so that's the idea. And so here, I want you to try this. You don't have to go out and buy a bunch of candy. But what I want to suggest you try is here's what I do. I could create 100 candy population, right? And what I could do is I could basically set my population. And so do this mental exercise, or even go out and do it. Or you could do this with the stuff in your kitchen, right? Grab a bunch of food, right? Grab a bunch of food items, at least 50 of them, and you can even do it over time, or and grab a bunch of things and just keep track of how many calories everything has, right? I've got 6 granola bars, each with 100 calories. So those 6 granola bars each have 100 calories. I've got 3 boxes of cereal. A serving size is 65 calories. And try to identify a population of food, right? And if you do this, then assign every food item a number, and then randomly sample from your food items. You'll come to find that your average for your sample, as long as you do it randomly, will look like the average from your population. I like to do it with candy. It's kind of this fun thing that I do, but you can do it with anything, right? Anything where you know the population and just start randomly sampling from it. Or there's online random number generators. You can come up with 100 numbers, right? In Excel, do that. Open Excel, come up with 100 random numbers in Excel, and then have Excel tell you what the average is for those 100 numbers, and then start taking random samples of 10. What you'll find is that your random samples have averages that look darn close to your population average. And so just try it. I encourage you to use candy. Get yourself a bag of 100 candies and try it, or grab yourself 100 numbers that you come up with and start taking random samples from it. And you'll find that small samples can, in fact, look like big populations as long as you randomly sample. Or you can just memorize the rules and take my word for it. So the big message, once again, is if you use careful random sampling procedures. Now, what are those careful random sampling procedures? Define your population well. Actually, for example, I'm interested in LA firemen. Define my population well. actually grab a sample of firemen at random from that total population where each fireman has an equal chance of ending up in my sample, then I can use that sample of firemen to make decisions about firemen across LA. You can draw conclusions about populations based on samples, as long as you sample them randomly from the known population. And so now we have our first tools to put in our toolbox of evaluating inductive evidence, the quality of research. You could ask a research study when you read it, who did you do your research on? Is it a convenient sample? Well, I guess you can only make decisions about those kinds of people. Is it a random sample? Well, then that's going to be much better, more high-quality research than research done on convenient samples, right? Random samples. Who you did your research on matters. And the nature of your sample determines who you can make decisions about. And the best samples are random. Big samples from well-defined populations sampled randomly. All right, that's it for this discussion. I look forward to chatting with you all next time. And once again, if you have any questions about sampling and sampling procedures, please leave those questions in the forum entitled Sampling Forum so everyone can benefit from your questions. See you next time.